very interesting. And what I picked up in the last couple of answers that you provided as well is that with Bitfusion, the primary focus has been on both CUDA and I think as well OpenCL from that point of view, right? But that kind of limits the customers as well as what they can do with the framework. Now, I think that's where it becomes interesting because at VMworld, we actually spoke, or I probably should say you and the team spoke about a new project that you're working on. And I think that is something that probably a lot of customers that now are already looking into Bitfusion or maybe looking into Bitfusion in the future will be interested in. And that product, of course, is product Radium.
So at a user level, from the perspective of the user, Bitfusion allows you to get high performance computing without writing code for high performance computing, right? You can run your models attached to GPUs, you can run locally on your CPUs, but it allows you to attach and detach resources on the fly. You don't have to worry about DevOps. That's sort of separately managed by your admin or DevOps team. And all you have to do is attach and detach. And so that burden of managing infrastructure, one of the things that's important today is this idea of self-service, right? The ability of consuming, the end user consuming and driving the usage of infrastructure by themselves, right? Without having to call up an admin for permission or whatnot, or for an allocation. And so Bitfusion separates those concerns. The user can focus on what they need to do to be productive, and the admin can simply manage the scale and the size of the resources that they deploy, right? Now, Bitfusion was really a good technical feat in that we proved that it's possible to get high performance over a network, and to have that separation of concerns, manage the infrastructure versus the application itself. Now, what we'd like to improve on Bitfusion is a few things, right? Number one, Bitfusion is tied to CUDA. It's tied to a proprietary API from NVIDIA. And basically, whenever a new version comes out, we have to think about revalidating, recertifying, running our applications. Sometimes there's a bug. Sometimes there's a new feature that's not properly documented or expressed, that sort of thing. And so we have a part of our team that's just simply working on CUDA compatibility, right? So, in this era where you have really a multitude of new vendors coming out with better hardware, in fact, there's many hardware vendors that can show 2 to 5x better performance or better efficiency than the latest generation GPU, simply because they're tuned for the AI/ML workloads today. We want to be able to take advantage of those for our customers, right? So there's actually many vendors. There's hundreds of new architectures today that can be leveraged for different phases of the application. We want to be able to take advantage of those, not just GPUs, right? So in order for us to do that, we have to rethink how we do application capture and library interposition the way we do Bitfusion. Second thing is performance, right? Performance is extremely key in any virtualization component. And what we've noticed is that the evolution of compute over the last, I would say, 10 years from CUDA 4 in 2011 to now, is that the compute devices, whether it's GPUs or any other sort of accelerator device like an IPU, the accelerator and the CPU are becoming more and more coupled with memory, right? So it's no longer master slave or sort of like a stateless offload device where you're explicitly interacting with that device with explicit buffer copies and explicit synchronization primitives, etc. Now it's all about memory. The GPU can actually read and reference allocate memory that's allocated by the CPU and vice versa. So imagine you come up with a fancy data structure on your application code. You can hand that to your GPU. Your GPU can just use it without any explicit data copies, right? So that is unified addressing, unified memory, managed memory, and so in CUDA 8 in particular, this is where that became really mature. Now the GPU device and the CPU device can actually execute computational graphs, whole expressions of computation, stages of computation together without any other intervention. So think about, executing a set of computations, coming up with a computational graph. It's both visible to the GPU and CPU because they see the same memory now, and they can independently work on different parts of the graph together, right? So now what you see is, instead of less coupling that's useful for network attached devices, now you see more coupling.